So the last topic I wanted to talk about qualitatively, in the book it's talked about quantitatively as well, is something called absorption refrigeration. And this is where we use heat to create cold. Absorption refrigeration systems are what are used in large office buildings where you have hundreds of tons of air conditioning refrigeration that needs to be done. You're not using the vapor compression system, you use something called absorption refrigeration. And basically a pump is used to create the pressure difference between this, and it's often used for units with 100 plus tons of cooling. And sometimes water can be used as a coolant, so I could use water as a refrigerant, which seems a little bizarre. But if all I want to do is air conditioning something, if I had water at 50 degrees Fahrenheit, then I could use that as a cooling source and I'd circulate air over it, and I don't need the air to be at 30 degrees. I really don't want it even at 50 degrees. So, and there's something called a lithium bromide system. And there are other systems. And so it uses, let's say, water at 50 degrees Fahrenheit. The pressure P is equal to 0.178 psia. So this lithium bromide system operates at a vacuum, so the issue of air leakage in is a problem, and so we're looking at running at a low vacuum, because 14.7, so this is, let's see, I did the calculation, about 29.5 inches of mercury vacuum, so it's a very significant vacuum that we have to run the system at. The text talks about an ammonia water system, and with that I can use ammonia as a refrigerant, and I can achieve low temperatures as well as temperatures for air conditioning. The principles are the same, and let's see how this works. But the big deal is I'm using heat to create cold, so I'm using much less power, I'm using bigger systems. So this is figure 16.25, 23, and it's an ammonia water system. And so in this system, the ammonia is the refrigerant, and now let's see how this happens. So we're going to have something called the refrigerant R is NH3, and we'll see C is for the carrier is H2O. And R for refrigerant, so the carrier carries the refrigerant. And so now if I draw this system, I have the condenser. So that's, we're familiar with the condenser. I'm going to have NH3 enter it. It's going to leave it, go through a thermostatic expansion valve into an evaporator. And this is where I have my Q dot in. So this is where the cooling occurs. So this part, and obviously I have Q dot out here. So I have that. So this part looks familiar with what we've done. But now we're going to do something that's different, which makes this different. So now I need to draw a couple more items. One is a generator, and the other is an absorber. So the ammonia, so now I have coming out of here, I have the ammonia, so I have R. The ammonia comes out, and it's going to go into something that we call an absorber. So it's going to go into the absorber. We're going to either have heating or cooling going on here. And I'm going to take a pump. So now I have a pump. So what I have in this right now is I have water and ammonia. So I have R and C. So I have ammonia and water in here. I'm going to take a pump. It's going to take suction out of here. It's going to discharge it into a generator. And this is a generator. So that's what that is. And so what the idea behind this is, I have ammonia and water. If I heat the ammonia-water mixture, it drives the ammonia out. So in the generator, I'm generating ammonia. So coming out of here is going to be ammonia. So I'm going to have coming out of here is my refrigerant ammonia, and I have that happening because I'm putting Q dot in here. So I'm putting heat in, so this is the heat in to create the cold. And the pump is creating a pressure differential, so rather than a compressor, I'm using a pump which uses much, much less energy. And so now, so if I, let's say I start here with the generator. So with the generator, I've driven out the ammonia. So now I have a high temperature liquid that has mostly water, but it's at a high temperature. So now I have P high, and T high. So, and it's this carrier, and now I have that come back, and I bring it back here. So now I'm going to bring that back into the absorber. So now I have, this is low R in C. So I don't have much ammonia in here, but this is all ammonia. So now the cold ammonia comes back and mixes into the water. I have it go into the water, and there's either, it depends on when it's an endothermic or exothermic reaction, whether I have to add heat or cooling here. And so I have that going on, and now I have something that's at a low temperature, but I have a high amount of refrigerant in here. I pump it back, I add heat, drives out the refrigerant. This process is our normal cycle. Now I go through here. I'm going to have a valve in here somewhere to reduce the pressure. So I have this high pressure. Now I have to reduce the pressure. Comes back here, low pressure, pump it up, and the cycle completes itself. So this is the ammonia absorption system, and the other absorption systems work in a similar conceptual fashion. And the coefficient of performance, COPC, is equal to Q cool over, I'll make it a Q dot heat. So I'm putting in heat, I'm creating cool, and it's a different concept. And so there's an example problem done in the text that goes through this in great detail, but it's worth a week and a half of figuring out, so we're not going to do it in this course.